Okay, we're moving on to 9.3 and 9.4. So I'm putting these together because we're going to pretty much do everything we did in the last couple videos, but just adding it to 3 dimensions. Now, what is that going to mean? So to start, it's going to change the notation a little bit. What do I mean by that? Is now the vectors that we look at are going to be, so instead of having a sub 1 and just a sub 2, we're going to have a sub 3. So it's going to have this additional component. Same if you look here, we'll talk about how to find the component form, right? Having an initial and a terminal point. If you notice, all we're adding is that additional z coordinate. So points in 3 dimensions have an x, y, and now a z. That's all that's happening. We're adding that additional point. Same thing with vectors in form of ijk that I just showed. It's going to be a sub 1 I, or I'll just do a. Oh no, a sub, sorry. A sub 1i plus a sub 2j plus, and then this is the third part, we're adding a sub 3k. Right? And there's not a lot changing. Everything is pretty much staying the same. Let me just show you visually what that means. So we always had our x and y axis, but now we're going to have the z axis as well. So this is my y, this is my x, and then this one going straight up now is my z. Again, everything is still pretty much the same. For example, we still have vectors. They just have the way the vectors are made up. They are made up in 3 portions. We're going to go in the x direction, in the y direction, and then the z direction. So that's all that's changing, is this additional coordinate. And for this ijk notation, again, all that's happening is now we're just extending that geometrical interpretation to one more vector. So the initial point of k goes on the terminal point of j. The initial point of j goes on the terminal point of I. So it looks something like this. You'll have a vector in the k direction, in the x direction, which is I, the y direction, which is j, and then k. So you see, terminal, initial on terminal, initial on terminal, and then you'd go from the first initial to the last terminal to make your vector. That's why we still have this ijk notation. I don't expect you to graph any of these, but we're going to go through everything we just did in sections 1 and 2, but now we're just applying it with this additional term, with this additional point, right, with this additional component. And you're going to notice a lot of the same definitions. So here it says the component form of a vector is represented in a space with initial point P and terminal point Q. Now all I did is add the z point, right? And then to find the vector between the 2 points, you just do, remember what we said, final minus initial, final minus initial, final minus initial. And that's all these little formulas here. And this is when you don't have a vector, but you're trying to find a vector between the 2 points. And that will give us, so let's call this vector v. That's going to be, and remember, you have to make sure it's the terminal minus the initial. So 3 minus 1, then it's going to be 1 minus -4. So it's important to know that there's a minus that's coming from the formula, and there's a negative coming from the coordinate. And then we have -1 minus 5. And then here's my vector. I have 2. That's going to become 5. And then -6. So again, all I did is just same work. Just did it to one more point. That's all. But this is still a vector, it's just in 3 dimensions. Right? And then doing our algebraic operations. Remember, you did them, you added or subtracted or applied the scalar multiplication to each individual coordinate. Sorry, each individual component of the vector. So, to find the sum of these two vectors, I didn't put any specific thing to find. So let's find 2u minus v. So what does that mean? So 2u, I'll just do the scalar multiplication first. That's going to give me a vector that's 2 minus 4 and 8. All I'm doing is taking that 2 and multiplying to each component in u, right? That's what scalar multiplication does, different than the dot product. And now I'm just gonna, now there's 2 things you can do. You can either distribute the negative into v, right? Or you can just subtract 2u from each component of v. But if you distribute the negative, that means then you're going to add the vectors versus subtract them. But to keep this nicer, I'm just going to take the vector 2u, which is going to be 2, and then I'm going to subtract it by 6. And then -4 minus -1, and then it's going to be 8 minus 1. Now you want to be careful. I know we might accidentally be looking here, but remember, we're doing 2u minus v. So I applied the 2 to each component of the vector. So that's what we got, 2, -4, and 8. So that's what I'm doing. And then v is subtracting to that new vector. So it's 2 minus 6, -4 minus -1, 8 minus 1. To give us the vector -4, comma -3, because right, these two negatives become positive, and -4 plus 1 is -3, and then 7. So again, that's why I'm putting it all together, because we're literally just doing the same thing, just one more time inside of the vector. Same thing for magnitude, right? We took each component, we squared them, and then we added them together. Now for all we're doing next is adding one more additional point. So for example, doing the magnitude of this vector is the square root, now 3 squared plus 2 squared, and then I'm just doing now the last component, right? That's the component, 25 squared. So what does that give me? That's going to be the square root of 9 plus 4 plus 25. And that's going to be the square root. Oops, I made that too long. Square root of 38. And I can't simplify that any further. That's going to be my length of this particular vector. Right, and that's pretty much what you see in 9.3. I should add or, right? I could have just as easily have said that u is 3i plus 2j plus 5k, just so we get used to that ijk notation as well. And then we have the dot product again, which we just went over. All we have is, again, one more additional component. So there's not a lot to this. It's just that one extra component. And the way it worked before, remember, we multiply the corresponding components, but then we do the sum of those products. So to get used to that ijk notation, so I didn't say u is this vector and then v is this next vector. I just say do the dot product of these two vectors, and that's going to give us it's going to look something like this. So it's going to be 2 times -1 plus -3 times 2 plus -1 times 3. Remember, the dot product of two vectors is the scalar. What I mean by scalar, it just said that we're left with a number. Versus scalar multiplication, you still have a vector, right? What we did in this previous example here. Multiplying 2 to the vector u, it's still a vector. It just doubled the length of that vector. Doing the dot product here just becomes a number. So this simplifies to -2 minus 6 minus 3 and leaves us with -11. Now we learned this version of the dot product to help us with the second version when it comes to when it comes to finding the angle between the two vectors. So you can either start with this formula, isolating cosine, solving theta, by isolating theta by using cosine inverse, or you can go jump right into your cosine inverse. But to do that, we need to have the dot product of these two vectors, which again is going to be 2 times 5 plus 2 times -4 plus -1 times 2. Now that's going to be 2 times 5 is 10. 2 times -4 is -8. Then -1 times 2 is -2. And that's going to give us 0. Right? And then we need to know the magnitude of u, which is going to be the square root of 2 squared plus 2 squared plus -1 squared. And that's going to be the square root of 4 plus 4 plus 1 is the square root of 9, which is equal to 3. the magnitude of v is going to be the square root, right? We just take that extra component, 5 squared plus negative 4 squared plus 2 squared is equal to 25 plus 16 plus 4, which is going to be the square root of 16 plus 4 is 20, plus 25 is 45. Now putting these values, just to save some space, I'm going to erase these. I hope you saw that. Just to give me a little bit more room. To take everything, right, and be theta is equal to cosine inverse of 0 over 3 times square root of 45. And I probably could simplify 45 to a different radical, but because we have 0 in the numerator, I know this is just going to give us cosine inverse of 0. And when does that happen? When is cosine 0? Right? Because here we're given the terminal point. We're trying to find the radian. But since we're looking for an angle between the vectors, I'm looking for a degree, and that's going to be 90 degrees. And remember, when two vectors have a 90-degree angle between each other, you would say that they are perpendicular to each other. Or there's another word that gets used in math quite often, and it's the word orthogonal. So two vectors are orthogonal if they are perpendicular to each other. And if you notice, I didn't really have to worry about the denominator of this formula, because just from the dot product, that gave me 0 in the numerator. Getting 0 in the numerator is automatically going to make everything 0. So there are some definitions that say that two vectors are perpendicular to each other if their dot product is equal to 0, because this part will happen every single time. Now, if we had another number, well, one thing to always check the moment you introduce inverses, if that number is in the domain of cosine inverse, which in this case it is, and then you can proceed to find the angle between. Here, you might need a calculator, but because it was 0, I didn't need one because I know exactly how to get 90 degrees. But that's pretty much what I'm going to look at for 9.3 and 9.4, is being able to do all the same things we did before, but just adding that extra z component. And for the next video, we're going to talk about, since we're leaving off with this idea of being orthogonal or perpendicular, in 9.5, we'll talk about this idea of a cross product that given our two vectors, it finds a third vector that's perpendicular to each vector in question. So we'll discuss that on the next video. And again, these aren't too bad. It's all very algebraic. If you notice, just adding, multiplying. So these aren't too difficult.